Hi, welcome everyone. Thank you for joining us on the second session on novel machine learning approaches. I'm Linas Baltrunas from Netflix, and I will be your chair for this session. If you have any questions, please post it on the WUVA entry for particular presentation. And I would appreciate if you could do it early on so other people could upvote it. And also it would refresh on time so I could ask them. We have a tight schedule here, but I encourage you to follow with the speakers and continue discussion after the session. And the authors will answer your questions even if we don't have time to answer them during the session. The first speaker is Gustavo Peña from TUA Delft. And Gustavo, take it away.
Yes, thank you. So hello everyone. I'm going to talk about our paper now on performance estimates. This is joint work with Rodrigo when I was a master student at UFMG. And first I will talk about two related areas. So the first one is performance prediction, and also I will talk about ensemble learning. So first, performance prediction. So this is a big field in information retrieval, and basically the idea is that given a model, at least in ad hoc retrieval, is to given a retrieval model in a query, we want to predict the effectiveness, for instance, the NDCG of this combination. So we are predicting the effectiveness or predicting the performance. In recommender systems, this is also a thing. So similarly, we have a recommender and a user, and we want to predict the performance of this combination. So I'll give you an example of a simple performance predictor. So here we want to capture the intuition that a user that has more data to represent, will lead to better models, to more effective models. So this first user here has 3 ratings, while this second one has only 1. So we'll call this performance prediction the number of ratings. And if we use this, we would say that the first user would have would lead to higher effectiveness. So the performance predictor is 3 for this and 1 for the second user. So moving on to ensemble learning, it's basically a field of machine learning where we try to combine several base learners, and we do so to improve the effectiveness as well. So we want to have better generalization as compared to using only one learner. And a specific type of ensemble that is important to our work is called stacking. And in stacking, if we are talking about recommender systems, we will have several base recommender systems. Each one will output a prediction, and the stacking or the ensemble will receive those ratings as the input space, and it will learn a function that will map from this input space to do the final prediction. So this is what won the Netflix prize, and a lot of KL competitions are won by ensemble, by stacking. I think on the Twitter competition of the RecSys this year, there were some stacking approaches as well. Another key idea here to understand our work is that we can enhance the stacking with, besides the base recommender systems, we can also use as additional features the performance predictors. And the stacking will take this input space now. So the idea here is that this will help the ensemble to learn better functions. So for instance, if a user has few ratings, the example we showed before, and the ensemble will know this because of some of the performance predictor that tells us this, it might choose the ratings from a content-based recommender rather than collaborative filtering, if that's the case. So this field is concerned of engineering those features, those performance predictors, so that we can have better stacking models. And our approach is a little bit different than performance predictors. So the key idea is that we want to, instead of handcrafting those features, we want to estimate the performance directly. So we do that by using the user's historical ratings. So it's quite simple how we calculate the estimates. So we use an evaluation metric, for instance, NDCG. We need a recommender, a base recommender system, for instance, matrix factorization, and we use some historical data from the user. So here we train this model on some data from this user, and the performance estimate is basically the NDCG of this model for this user using this data. So the idea here is that if we have one estimate of performance for each of the base recommenders, we'll make the life of the ensemble easy, because we are telling that the first recommender, we think it's going to be effective, the second might not be, and so on. So the stacking model could learn the interactions between those and make the final prediction. So our research questions, and I will talk a little bit about the experimental setup, but the main research questions we wanted to answer is how effective are the performance estimates for ensembling recommenders, and also how robust they are if we change the function that takes the performance estimates as input space. So if we change the machine learning model that we are training based on the scores of the base recommenders. So the setup, we have implemented 12 different performance predictors from previous work. It's sort of a baseline for us. We combined 32 different base recommender systems. We use some variations of the same as well, changing some hyperparameters. And as I explained, we have one performance estimate for each of those base recommenders. In our experiments, we compare 8 different machine learning methods for the ensemble. And then the main comparison that we do here are the 3 input spaces. And this is like stacking. And the second is stacking with performance predictors. And finally, what we proposed, stacking with the performance estimates. So before I dive into the main comparison, I will talk about some hyperparameters and their results when we change them. So if you use the evaluation metric for the performance estimates as NDCG, we see here the performance, the final performance of the ensemble on different data sets here. And we see that if we use a root mean squared error or other functions that are not based on the list, we have better effectiveness when using the performance estimates. And this is one of the hyperparameters, let's say, of the performance estimate. Also, another important hyperparameter is that we want to use the weighted variation, because if we use the unweighted one, the performance estimate will just be about the users and not about the users and items. We have more details about that on the paper. But let's go to the main results, which is what input space is more effective, and if it's robust to different learning algorithms as the ensemble. So here on the x-axis, we have a random forest, which means that we use all the 32 recommender systems as input for this random forest, which will output the final recommendation, and then we achieve this NDCG. B means that we are using both the performance predictors and the base recommenders, which is slightly better. And if you use the performance estimates, we see that it's even more effective. And if now I'm going to display here all the different ensembles that we tested. This is all for the Amazon Books dataset. What we see here is that for pairwise and listwise models as the ensemble, we achieve the higher effectiveness. We see that the gap is bigger now for the performance estimates. And yes, that summarizes the main findings of our paper, that the performance estimates are indeed an effective approach, and they are quite simple. They do not require handcrafting features, which are the performance predictors. And that was my presentation. Thank you, and I'll be glad to answer any questions.
Thank you, Gustavo, so much for your presentation, and we have time for a couple of questions. So first question, do all 12 performance estimators use the same historical rating data set? Do you use content features or just behavior data?
So on the paper, we only test ratings. We only use ratings. We don't use any contextual data. I think that was the last part of the question. The first is about if we always use the same data. Am I correct?
Do all 12 performance estimators use same historical rating data set? Yes.
Okay, yeah. So we have 12 performance predictors. They all use the same data, as well as the performance estimates. They all use the same data.
I see. Thank you. There is time for one more question. So maybe it's from my side. So in the recommender assemblies, the output of the first level model kind of becomes features now in the second level model. So can you explain a bit like why, when we do normal machine learning, we don't do performance estimators for the features themselves, and why when we do assemble, it helps?
I think the idea here is that if we are only talking about a single model, knowing that it's going to be to have bad effectiveness or low effectiveness, we can change this. But if we have, for instance, two models, we know that the first is going to be better than the other. We might use more of the second one in this case. And on the next example, we might use the other one. So if you're combining models, I think this is important. If we are using only one, I'm not sure what you can do. It's like, okay, I know that this model is going to be bad, but I don't have another option.
I see. There are a couple of more questions. Why do you think the effects are so strong for pairwise methods relative to pointwise methods?
Yeah, that's a good point. I'm not entirely sure why they're better. I think the pairwise and listwise models, they have more capacity, and then when we feed them with those features, they are able to learn even more from that type of data. But yeah, I'm not sure why the gap is so higher when we use listwise and pairwise models.
Thank you. And we have time for one more question. The performance estimates are calculated at training. Are performance estimates calculated at training time? And do you have any thoughts what to do with the new users, like cold start problem of new users?
Yeah, so they are calculated during train time. We train, and offline we also estimate the performance using some data. On cold start users, this is not possible because we do not have historical data. What we could do is use some sort of other type of cold start features that could indicate the performance as well. So maybe we see that the model is underperforming for some regions. So if the user is from this region, this could be helpful. Instead of being specifically about users, it could be broader, I guess.
Okay, thank you so much again, Gustavo. And let's go to our next speaker, who is Chang from University of Amsterdam. Chang, take it away.
Okay, thanks for the introduction. Just give me a second. Okay, hello everyone. Welcome to my talk. My name is Chang Li. Today I'm going to discuss our paper, Cascade Hybrid Bandits, Online Learning to Rank for Relevance and Diversity. This is a joint work with Haoyun, who is from Bloomberg, and my supervisor, Maarten. Let me start with a simple example. Thinking we are doing the online recommendation, we have an atom candidate sets, saying now we have 12 atoms. Different colors means the atoms comes from the different topics, and the number of dots on the atom means how relevant the atom is to the user. And the job we are thinking is as following. The recommender system show a ranked list to the user. User follow a certain type of click model and then click on the displayed ranked list, and then the recommender system learn from this click behavior. There are general 3 properties in our problem. The first one is the position bias, and where we say a user focus more on the top ranked items. The second one is relevance ranking, where in our recommended results, we want relevance items to be on top. And the third part is the result diversification, where we want the recommended items to be diverse. And we will address this one by one. For the position bias, we assume a cascade model to explain the position bias. And here, for example, in this ranked list R, a user will browse the item from top to the bottom and click the first attractive item and stop browsing the rest. So here we have each item has an individual attraction probability. Here we call it alpha. And R1 means the item rank on the top position. And user follows the top-down browsing and single clicks. This model is simple, but it's an effective way to transfer the click feedback into the training data. And also the goal of this cascade model is to maximize the probability of clicks. And for the second part is the relevance ranking, where we assume each item can be represented by a feature vector. Here we call it Z. And we also assume a user has their individual preference. Maybe we call it beta star. And when we do the relevance ranking, we just do the dot product and sorting with respect to this item relevance. So probably one potential ranking of our example is like this. Well, one problem here is if we only focus on the relevance ranking, maybe the result list is not diverse enough. For example, in this case, we are missing the yellow cube. Here we think about the result diversification. Here we use a submodular model to do this. So think about this. We can think each item can cover a set of topics. For example, a cube covers 3 topics, red, green, and blue. And it covers part of the topic. And then we add another item to the ranked list. So another item can also covers another topics. And as a ranked list, we are talking about what's the topic coverage of the ranked lists. And this can be modeled by a submodular model. By saying submodular model, we mean if we add a new item to the ranked list, the topic coverage will not be decreased. And also we add a similar item to the topic coverage to the ranked list. The topic coverage will not gain a lot. An example here is we can do the max of each individual topics. And then the topic coverage of the ranked list will be this. And for now, when we are building the ranking, now we have 2 items in the ranked list. We want to talk about the gain in topic coverage. Here we call it the delta. So when we want to choosing the third item, the topic coverage of the third item depends on the first 2 items. So it's just like this, right? So here in this example, thinking like we have a ranked list with this blue and red items on top. And when we want to choose the third one, probably the yellow item will have a large topic coverage gains. And also we think a user has its own preference over different type of topics. And then we do the dot products and find the item to include in this ranked list. So now we choose a yellow box as the third one. So combine the 2 opponents together, it comes to our hybrid model, which balance the relevance and diversification, right? So given a ranked list, we assume an item can be represented by 2 parts. The first one is the relevance feature. The second one is the topic coverage. And also for a user, we assume the preferences can be captured by two parts. One is relevance part, one is interest for the different topics. And then we do this dot product and sorting with respect to this balanced ranking score. And then probably in our example, we will reach to a ranked list as this. So here we can say the relevance items are on top, and also the results are diverse. Of course, the goal is always maximize the the probability of click. So let's say how our algorithm work. The algorithm works in rounds. At the beginning of each round, the algorithm will estimate the user preference. And then when building the ranking, the algorithm starts with an empty ranking. And for each of the remaining items, the algorithm will compute the optimist estimates on the attraction probability, or we can call it upper confidence bounds on the attraction probability of the remaining items. And then put the most optimist item in the rank list. And then we repeat this process until we reach the enough items. Then we display the rank list to the user and observe the feedback. So we use this feedback to update our algorithm. In the paper, we show some theory. We theoretically bound the regret of the proposed algorithm. We call it cascade hybrids. And here K is the number of positions, N is the running time. And this bound is comparable to any linear bandit-based bounds. By seeing the regret, we mean while we are running the online algorithm, the difference in terms of number of clicks of our algorithm compared to the optimal ranking policy. So the lower regrets, the better. And then we conduct an empirical evaluation on two tasks. The first one is movie recommendation. So in the left plot, we say here the K means the number of positions, D means the number of topics. Lambda here is a parameter for our simulator. This lambda is unknown to all algorithms. So different value of lambda can control the balance between relevance or diversity of user preferences. On the red line is our algorithm. We say our algorithm is better than others. And on the recipe plots, we say when we choosing different value of lambda, our algorithm still among the best. And by the way, some of the baselines are focused on relevance, some of them are focused on result diversification. So we can say our algorithm still always on the bottom line. In the second task, we focus on the music recommendation, and we observe more or less the same results. Now let's conclude the paper. In this paper, we formulate a novel online learning framework which considers both position bias, relevance ranking, and result diversification. And we call this problem cascading hybrid bandits. And we propose the cascade hybrid algorithm to solve this problem. And we show the algorithm is theoretically efficient and also is empirically efficient. And so at the end of the presentation, I just have an advertisement for myself. I'm still looking for a job. I'm a final year PhD student. And that's all for my presentation. Thanks for the attention. I'm willing to answer all questions.
Hey, Chang, thank you so much for your presentation. And while we are waiting for other questions, maybe I will give you one. So you have some assumptions on the diversity metric that you are using. And I wanted to ask you, do popular diversity metrics that are used in literature, follow these assumptions? I don't know, some examples, centralist diversity, query aspect diversification, and so on. Is it easy to extend them to meet those assumptions?
Well, the thing is, actually, when we design this algorithm, we don't consider a lot about these assumptions. These diversity metrics, because we purely focus on how to improve the click-through rate. And the way we design the click-through rate, we think when user click items, it depends on both how relevant the item is to the user and also how diverse the ranked results. So if the user prefer a diverse ranked results, and then the rank list from the algorithm are diverse. If the user prefer relevance ranking, the results from our ranking algorithm will be relevance. That's the main idea
Cool. Thank you. There are a couple of more questions. So one of them is, how do you obtain upper confidence bound for individual item predictions?
Oh, yeah. I think I didn't show it in the algorithm, but the upper confidence bound is based on the UCB. It's a variation of Lin UCB algorithm. Like there are some equations back there. I didn't show it. Yeah. Okay. It's based on Lin UCB algorithm. Yeah. It's a variation of it.
So it's in the paper. Could you maybe answer on the question directly on the platform after the talk?
Yeah, sure, I will. Yeah, because it's some equations, it's more easy to check it on the papers. And yeah,
perfect.
Sure, I will.
And one more question. How many episodes would be required to learn a single user diversity preference? Is there a lower bound?
No, here, so in this paper, we didn't derive a lower bound, but it really depends, right? So generally, we need at least, we need quite a lot of clicks seeing several thousands episodes, and then we will know the user's preference. Yeah.
I see. Thank you. And one more question. Mm-hmm. Do you have any ideas about how robust the algorithm is to the amount of diversity user desire?
So how robust the algorithm is to user diverse desire? I think, if I understand this question correctly, I think if the user really prefer diversity and our algorithm our algorithm is able to show a very diverse ranked list. I'm not sure whether this is robust or not, but it really depends on users' preference. Yeah.
Okay, thank you. If you have any questions, please post it and author will answer them. Thank you, Chang Li.
Yeah, thanks. Wait, let me. Okay, thank you.
And our next speaker is Ahmed Rashed from University of Hildesheim. Take it away.
Thank you. So, welcome everyone. I will be presenting our paper with the title MultiRec, Multi-Relational Approach for Unique Item Recommendation in Auction System. So, this work is in collaboration with Volkswagen Financial Services. So, let me first talk about what's the problem with auction systems. So, for example, in used car centers in Volkswagen, we have a traditional interaction between dealers and used cars. And in this case, let's say we want to build a recommender system for dealers that will be recommending used cars for them. And in our case, in auction systems, we have a problem where items can only be sold once. So a dealer can buy a car and that's it. The car cannot be sold again. And this means the interaction vectors of the dealers are unique. And this means also that the car, we cannot rely on car ID. And this also means that traditional techniques that rely on the interaction graphs between dealers or users and items, in this case, is not feasible. And also techniques that use only IDs of the user and dealers won't be feasible, and they have to be extended. So this means also that the interaction matrix is extremely sparse because items can only be sold once, and that's it. And we have less information to use for new items. So our proposed solution consists of two phases. So the first phase is to try to leverage any auxiliary relations that exist in our data, such as the bidding interaction. So usually in auction systems, you have dealers or users bidding on item before purchasing or they get sold. So leveraging this information or this lower level implicit feedback signal can give us some information about the user interest, which usually contain more information than the main relation. For example, here, it's a purchase relation. We have also the sale prices, which also give us some hints about the willingness to buy for a higher sale price. And of course, a lower sale price means lower willingness to buy the same item or similar item. And of course, since items are extremely unique, or technically there is no two items that are the same in auction systems, we have to leverage item attributes or content information. Otherwise, we can't do it because you can't rely on IDs in this case at all. So how we solve this problem, but before we go to that point, let's quickly explain the settings. So we have a set of users, and those users might have a set of attributes. such as a profile information, location, and so on, or what kind of brands or what kind of item categories they like or they bought before. So we have the item also, which are a set of items, and each item will have a set of attributes. For example, in case of Volkswagen, we have used cars, and those information contains more information about the cars, the engine, model, brand, and so on. And in our case, we had 3 interaction matrices or interaction relations, I would say. So first is a purchase relation. So a dealer bought a car. We have the bidding relation, which means the dealer bidded on an item before he bought it. And we have a sale price. So for which price exactly a specific dealer bought a specific car. And of course, this can be generalized to any user item interaction in an auction system. So, and in our case, the objective will be to predict the missing scores in the main interaction matrix, which is a probability to buy or the likelihood to buy, which is the purchase matrix, using all possible relations in this case. And of course, using the item attributes. So how we did that? First, we used attribute-aware nonlinear embeddings. So we simply feed the features through an embedding layer. So let's say in this case, FU is an embedding function, which can consist of multiple layers of fully connected layers, where we use, in this case, in case of users, we use the user ID and his attributes. So it's personalized, I would say, embedding function. And in case of items, since we can't use IDs, it just use item attributes. And once we get those information, or let's say extracted the latent embeddings from the users and items, we feed those embeddings into a scoring function. And the scoring function here, you can see, for example, let's say for YP, for the purchase, it's just an element-wise first, multiplication between the latent embedding, and which then is fed into a scoring function, which is in turn is just a series of fully connected nonlinear layers. And of course, we have also different scoring functions for different relations. And we have one main relation, for example, in this case, in our case, was the purchase relation. And we also, you can see here that we used multiplicative interaction between the latent features and not the concatenation, because it was much better in our experimental part, because of the multiplicative interaction and the alignment of features between the latent features of users and items. And of course, dot product function is also can be used in this case. So we can replace any of those parametric scoring functions with a simple dot product. And sometimes it was actually better than a parametric one. Okay, so to train such multi-relational approach, we simply use a giant loss across all possible relations that we have. So we have the bidding relation, we have the sale price relation, and we have the purchase interaction or the purchase relation. So for example, in the purchase relation, it's a probability, or it's just 1 and 0, either he bought it or not. So we use a logistic loss in this case. In case of the sale price, it's a default value or a continuous value. So we use the mean squared error loss. And in case of a bidding behavior or the bidding interaction, we also use a logistic loss. So we also have a binary interaction here. So 2 binary interactions and one continuous interaction. So how we train this model, we simply iterate in one epoch, we iterate over all possible relations. We draw a patch of users, and for each patch of user, we draw positive and negative samples if it's a binary interaction, or we just draw positive interactions. It's in case if it's a continuous interaction, continuous valued interaction. And we simply update the shared feature extraction functions for users and for items. And of course, also we will update the scoring function for the respective relation. So I think it's a fairly simple approach, and we apply this approach into onto 2 data sets. The first one is a proprietary data set from VFS. It's a P2B data set. So it's an interaction between dealers and used cars from VFS Used Car Center. And we had to find another data set for reproducibility. So people can also reproduce such kind of results and also can see the effect of using auxiliary information in this case. So we were lucky enough to find an ePay public data set. It's much smaller than the VFS data set, but you can still see the signals that we wanted to highlight in this data set. And it was really difficult to find public available data set, auction data set, because most of them were private and or didn't share the same characteristics of the VFS data set. So you can see here in case of VFS data sets, we have much more bidding interactions than the sales interactions, so much more information in case of biddings than in case of sales. But in case of ePay, actually, it's 16 times more information exists in bidding interactions than in sales. So sales are much, much, much smaller than the bidding interactions. And please keep that in mind, because I will highlight this part again in the results and how this affects the final results. So now we can jump to the experimental protocol. So we used the leave one out evaluation protocol, and we use the hit ratio at K and index GK as evaluation metrics. So in case of leave one out evaluation protocol, we didn't use the traditional way of sampling items. So we didn't sample items or negative items across all the data set, because this will give us an unrealistic metrics. Because in real life or in production phase, all items will be existing at the same time period. So what we did, we sampled the negative items from the same time period as a positive item in case of the leave one out evaluation protocol. Otherwise, it will give us a very high hit ratio and NDCG that won't match in the production phase. So we used also a couple of baselines. We used the random model, a top popular model, the DSM model from CIKM, DeepFM model, and NoIMF model and GraphRec model. So the last two models they were mainly rely on IDs. So we had to modify them slightly to use only attributes of the items. So we now compared those models against MultiRec. So you can see here that in case, for example, on funds of VFS data set, once we add, let's say here, the sale price and the bidding and so on, you can see large lift than just using the sale interaction, which is the main interaction metrics that we have. So adding auxiliary relation improves almost all metrics that we have here, in this case, hit ratio and NDCG, and it's consistent across all metrics and across all thresholds, but you can see the more threshold you have, or the higher the threshold you have, the lift start to decrease. So if you remember, I told you to put in mind the difference between the bidding, or how much the bidding is much larger than the sales interaction. In case of ePay dataset, it was 16 times more, which means that we have less information to learn from just the main interaction metrics. So you can see it here, the upper part is the models that was trained and learned from just the main interaction metrics. You can see now, once we add the auxiliary information, which is 16 times more than the main interaction or the main relation that we have, you can see an improvement that sometimes reach 135% in accuracy. So the more auxiliary relation you have, the more improvement you can get from your model. So here you can also see the impact of adding this relational data, or converting your model to a multi-relational model across different users or different dealers, in this case on the VFS dataset case, with different interaction frequencies. So you can see here on the leftmost side, we have dealers that has too few interactions or too few sales. And as we go to the most right part, you will see dealers with very high sales records or sales interactions. And you can see the adding relational information will consistently improve the model performance across all, or almost all kind of dealers or kind of users. You can see here also that the accuracy drops whenever we go to the left, to the rightmost part, because now we started to go into the domain of having profiles or dealers that are very noisy and buys everything, which is normal in this case. We call them brand dealers, which usually buy thousands of cars at the same time. So capturing the interest or the specific interest of those profiles is started to get more difficult in these cases. And that's why we see the drop here. Here we see the sensitivity analysis of the alpha weight, which is the weight of the different relations in the loss function. So you can see here, for example, it's different across the two data sets. The eBay dataset is much smaller, and it's much difficult to find the best peak or the best point for those two hyperparameters. But for example, in VFS, it was much smoother and much easier to find this best weight for those two hyperparameters, which means the more data you have, the more stable your model will get, and it's easier, or anyway, you will have to tune those hyperparameters for each data set and for each relations that you have. Okay, so as a conclusion, here we presented a multi-rec approach, which is, I would say, a very simple and flexible model that can leverage user item attributes. And it also can be extended for any auxiliary relations that you can have in your auction system. And it's not only constrained for auction system. So it technically can be applied to any recommender system setting where you have multiple auxiliary relations between user and items. For example, clicks, views, and maybe purchase, sales, or adding to this basket or so, and so on. So there are different relations that can exist in different settings, and this model can be applied. And this model, I would like to emphasize, this model is just the first outcome from the first phase of our project. So the objective of this phase was to build a very simple model, flexible model that can be put in production quickly and give a good result. So it has tons of possibilities to be extended, or there's tons of ways to extend it. So for example, you can extend it to add time factor or convert it into a sequence-based model. So the time was not included explicitly in that model. So what this one natural extension for this model, you can also add more external relational information if you have. For example, in this case, we still exploring the bidding price as another external relation. And of course, you can improve the embedding functions, for example, using stochastic shared embeddings to improve the embedding function. So there are many ways to extend this model. So this model is available at GitHub, and we also provide a script for pre-processing the eBay dataset for reproducibility. Thank you.
Thank you, Ahmed, for a great presentation. We have time for a couple of questions. So the first question is, did you observe any conflict between these three tasks while optimizing?
Not really, but you can see here from this part, this conflict is mainly solved by tuning the alpha weight. So for example, yes, of course, if you use a very high alpha S for the sale price, you will start to get bad results, I would say. So yes, there is conflict, and this can be tuned with the alpha weights. So giving more weight for specific relation, I would say, than the other relations, and so on. So it has to be tuned. And it might be in some cases that you will have to remove some relations that might not be helpful, or that might contradict the main relation you have. For example, you can have two relations between user and items, but one of them is exactly the opposite of the second. For example, one is click item or clicked on item, and one is did not click on item. And in this case, you can train the same model with the same, for example, scoring function or just a dot product. In this case, it will be misleading for this model, because dot product is just non-parametric version, and having two complementary or so two opposite relations will be confusing for the model. So yes, it can happen, but in this case, we didn't have such case, and alpha weights were enough to solve such conflicts.
Okay, thank you. Another question is, how do you think having much more or less rich item and user features in different, like in two data sets, affected the conclusions on either data set?
So in this case, the features for the VFS dataset was much larger. So you can see it here, I think. But in this part here, so we have around 700 features. In case of VFS dataset, that's not comparable at all with the eBay dataset. So adding more features for the items in this case specifically is more helpful. So the more features, the better the performance will be, because you don't have any item IDs. But in case of users or user profile, since we have the ID already of the dealer, of the user, and it's a personalized anyway, and we don't expect the dealers to vary a lot over time, it's not that significant. So the user feature are not that significant. The more significant is item features. So having more item feature in this case is the more significant part that you want to invest in.
I see. Thank you. One more question. Did you try to use nearest neighborhood methods as a baseline? And they are quite competitive for session-based recommendations.
Yes. So the problem with this traditional k-nearest neighborhood in this case, that users' interaction vectors will be unique. So you won't have two users with the same interaction vector, because items are unique. So you won't find any two users that have the same items or even common items between them in case of VFS. So, and of course, items won't have any interaction vector at all in this case. So use the traditional KNNs was not possible in this case.
I see. Thank you. And the last question from me, does it work on the first, price auction and the second price auction? And which one you tried?
This was a final price. You didn't explore yet because you mean this, the final price that will be get sold and the final bidding price. Am I correct? Or
so eBay, I imagined like second price auction. No, is the other data set is first price auction or no?
No, here we use the sale price, the final price. We didn't use the bidding price. The bidding price is currently being explored as an extra-auxiliary relation. Okay. But in this work, we only focused on the sale price, so the final sale price, which I think is the second best bidding price, or second top bidding price, if I'm correct.
Yep. Okay, thank you, Ahmed. And our next speaker is Kasper Hansen from University of Copenhagen. And Kasper, take it away.
Yeah, thanks. Yeah, thanks. My name is Kasper Hansen. I'm from the University of Copenhagen in Denmark, and this is work done at Spotify during last summer in my internship in collaboration with these amazing people. Our work is titled Contextual and Sequential User Embeddings for Large-Scale Music Recommendation. So first, let's have some motivation. So I would assume that most people in this audience would agree that recommender systems are essential for providing a good experience in streaming services, where in this work we are focusing on music streaming services, specifically Spotify. So for example, when you open the Spotify app or any music streaming app in the morning, you might be more interested in getting recommended some energetic music to get the day started in a good way. Whereas later in the day, you are perhaps tired and want some relaxing music. So the context can matter in this way, but also music recommenders face certain challenges. For example, tracks, they are often short and consumed together in sessions. It's not very often you only listen to one music track. Then the sequence of the past consumed sessions also matters a lot for what you're going to listen to next. And the content within each session is also highly contextual. For example, if you normally listen to music on your phone, but then suddenly listen to music on speakers, then it might be important in order to understand what kind of recommendations you want. Could be you're listening to music together with other people or even at a party. So in this work, we first do a music consumption analysis on a large-scale Spotify dataset in order to better understand this. And then based on this, we propose a new model called COSRNN for generating sequential and contextual user embeddings. And it's important to notice here that we're talking about embedding-based models, because we want to be able to utilize very fast news neighbor search in the embedding space, as opposed to perhaps more complex model that does pointwise predictions of a user and an item and then outputs a score. So let's look at the dataset. The dataset is from Spotify. It has around 200,000 users in a 2-month period from spring last year. And on average, each user have around 220 sessions with an average of 10 tracks per session. If we look to the left on the blue plot, then we can see the context distribution of each session. So we just define the context of a session as the context of the first track within that. So if that happens early in the morning, then the whole session is labeled as that. What we see is that, at least in this data set, most listen in the afternoon, as you would perhaps expect, but it's actually well distributed throughout the day. However, for the devices, we have that on this data set, 88% of the users use the mobile, but we still have 12% of the sessions appearing in the other contexts. However, if we instead of the distribution look at the proportion of users with at least one session in a given context, then we see that actually most users experience almost all of the time contexts except in the night. And even for the devices, we see that almost half of the users have used the desktop at least once, and also have some activity in the other ones. So this means that users do experience many different contexts, so we need to get this right. As we're working with embedding-based models, then we choose to also represent tracks as real-valued embeddings. So they are 40-dimensional and are pre-trained using a word-to-vec-like training scheme. In this way, we can also create session embeddings just as an average of those track embeddings. So let's look a little bit on the track variation within a context. So what we do is that we take all tracks across all users occurring in a given context and then compute the pairwise cosine similarities between these tracks for each context and visualize this using a box plot. So what we see is that sessions in the not so frequent context actually in most cases have higher cosine similarity compared to the majority ones, such as afternoon or mobile. So of course this shows that the music is a bit more similar across all users in these less frequent contexts, but also that there is some variation between the different contexts. Then we can also look at the session similarity between the contexts. So what we do is that for each user we take a session, and then based on the session embeddings we find the nearest session, and then we look at those two contexts, and we can plot that into a heat map, normalize the rows, and then we can get a probability distribution. Then since some users might only have activity, only listen to music in a few different contexts, then we also do a random sampling instead of the nearest neighbor and subtract that. This means that we get a probability difference heat map between sampling sessions ranked by the pairwise cosine similarity or based on random sampling. And what this shows is that if we have a positive number on the diagonal, then it means that sessions in this context are more similar to sessions also occurring in the same context compared to other sessions. So there's some session similarity for each user. So users listen to similar music within the same context. And this is especially the case for the devices, most notably so for the web. So now we've seen some of our analysis based on why context matters, that music is more similar within the context. Then let's look at the model we propose. So we call the model COSINN, which stands for contextual and sequential RNN. So recurrent neural network model. What this model is supposed to learn is a user embedding such that at a given time point, we maximize it such that the cosine similarity between the user embedding and the session embedding is maximized. And the way we do this is through learning a contextual offset embedding, which we combine or fuse with an aggregation of all the past sessions a user have experienced. So this aggregation, it's a weighted average and corresponds to a point in the space of sort of a global long-term embedding of where the general music taste of that user lies. And then the point of the model is to learn an offset to that point, rather than learning the actual point. The model as input takes session embeddings as the primary point. So we split a session in what the user listened to and what the user skipped. So it's corresponding to what the user likes and perhaps doesn't like in a session. And then we also, of course, have the current context. So that could be early morning and on the mobile. And then a number of features, for example, the number of tracks in the last session to know how long it is, the time since the last session, and then the stream source. And the stream source is specific to Spotify, so it could be how you listen to music. For example, if you listen to on a playlist or use the radio function. The way we evaluate this is in two tasks. So we have session ranking, which is how well can the model rank the current session above the last K sessions. And then similarly track ranking, which is how well can the model rank the tracks within the current session above the last K tracks. And we evaluate this on historic data where we have the 2-month period. And then for training, we use a lot of data in the front. And then for testing, we use the last 2 weeks. So we do a time split like that. Then for baselines, we have a number of trivial and then some state-of-the-art baselines. So first, as the user embedding, we can just pick the last session as being the user embedding. Or we could just pick the last session with the same context. Similarly, we could take an average. So we can do a weighted average of all the last sessions, or only an average of those with the same context. So the average of the sessions of all the previous sessions corresponds to the global long-term embedding we have in our model. And then we have the popularity baseline, which is just a session is popular if the computed by the popularity of the tracks. And then to get an upper bound on the performance, we have an oracle where we know exactly what the user is going to listen to, only half the tracks. And then 3 state-of-the-art models, RNN, latent cross, and GOD, which has been adapted to work in this embedding setting. Then, without going into too much details of the numbers, we generally see that performance improvements of upwards of 10% compared to state-of-the-art, in this case GOD. But we still notice that there's quite some gap between all the methods and then the oracles, so that even though it performs pretty well, there's still room for improvement for future work. Then if we specifically compare our model to GOD across the context, then we see, first of all, improvements across all of them, but also that we see larger improvements on the not majority context. For example, on the devices, we see larger improvements on desktop, speaker, web, and tablet in most of the cases, which could indicate that our model is better at learning the contextual differences that the user is interested in. So in summary, and you can read a lot more details in the paper, we have made a music consumption analysis where we show how context influences what you listen to. And then we proposed a new model called COSRNN, which are based on generating user embeddings that both matches the user's global taste, but also the contextual deviations. And this worked pretty well, as we saw upwards of 10% performance increases across different tasks and different metrics. And then, of course, it's always nice that these are embedding-based models, so they are fast to use in practice because we can utilize efficient nearest neighbor search, or even approximate nearest neighbor search if you want, instead of the models that are a little bit more expensive based on pointwise recommendations. So thanks for listening, and feel free to ask any questions here or on email.
Okay, thank you so much, Casper. And we have time for a couple of questions, and there are many, so please answer them also if we don't have time now. So first question is, did you happen to examine whether previous sessions are still predictive of the items if the new session comes after a period of longer inactivity?
So actually, we didn't look at that, but so we don't have the numbers, but we have thought a little bit about it. So what we can see actually in the results is that when we just consider only the last, I don't have my mouse, but if we only consider the last session as the user embedding, then it performs pretty well. But we haven't looked at what the time gap would actually mean. Could also in order to do that, we'd also need to take into account if a user only listens to music in a specific context, then it might be a whole day before you listen to music again, but it would be the same you listen to. But it would be an interesting analysis for sure.
Okay, thank you. Another question is, do you have a separate embedding for a skip versus listen?
No, so we can. So we present it differently in our model. In the lower part, the session embedding, so where we have listen and skip. So for modeling, we do split it, but at track, we focused on using sort of reusable track embeddings that could be used in all different kinds of downwards tasks. But when we do the modeling and make the user embeddings, then we do split it, and we saw an improvement when we did that.
I see. There are a couple of clarification questions. One is, what do you define as context? And very related, do you treat time context and device context independently or conditionally dependent?
Yes. So by context, we simply you can imagine you open the app, and then when you open it on your phone, then you have the mobile context, and it's early in the morning. So your time context is early in the morning. So for the modeling, we do have both. In the analysis, we only look at one of them at a time. We don't have a conditional analysis where we look at, for example, mobile usage depending on time. There we just ignore the other one. Okay, and one question from me. So why do you discretize the time context? Could you use just like raw timestamps, because you are using powerful, deep learning methods? Yeah. So that would actually be possible. We did that in the beginning. We didn't actually see that much of a difference when switching. So we chose this one because was a bit easier for the analysis, essentially.
Thank you, Casper. We are out of time. And the next speaker and the last speaker in this session is James Neve. Whenever you're ready.
Thank you very much. It's working, right? Okay, my name is James Neve. I'm a PhD student at the University of Bristol, and I'll be presenting my paper, ImRec, Learning Reciprocal Preferences Using Images. And this paper and my research in general is on reciprocal recommender systems, which is user-to-user recommendation. And this is used on social networks, on online dating services, for job recruitment. And it's quite different in a number of subtle ways from user item recommendation that you might have on Netflix or Amazon. And compared to user item recommendation, it's a relatively unexplored area in the literature, partly because of the difficulty with getting hold of data sets and privacy issues and that kind of thing. There hasn't been very much progression past KNN implementations. And last year in this stream, I presented on collaborative filtering for reciprocal recommendation. And this year I'm focusing on content-based reciprocal recommendation. So there haven't been a great number of content-based papers. The most recent one, I think, was basically the first one to introduce the term reciprocal recommendation to the literature, which was Recon, and that was about 10 years ago. And Recon makes recommendations based on categorical data. So, for example, age, height, weight, job, and so on. And this was reasonable back in 2010, perhaps, when the internet landscape was a little bit different. But these days, especially for online dating, services tend to have a lot more information at the disposal of the person searching. They have lots of photos, like free text profiles, and a lot of modern social networks actually designed for people to interact using photos and videos as their main medium. So we thought it would be very interesting to look at, especially photos, and see whether you can use that to predict potentially friendship and attraction. So the original contribution of this paper is threefold. Firstly, we create a model to predict personal attraction based on image data. Secondly, we design a content-based RRS, a reciprocal recommender system, based on personal attraction from images. And we demonstrate that our model outperforms the current state of the art, Recon, based on our evaluation. So just a few words about our collaborator. We collaborated with an online dating service called Pairs, which is the most popular dating service in Japan for this project. And it has about 10 million users, also growing in various Asian countries. And on Pairs, users are forced to see the photo, the free text profile, and the categorical data before they make their decision. So we do consider this a fair test against Recon for our evaluation. And one of the interesting things about reciprocal recommendation in particular is what do we consider evaluation criteria, right? For particularly online shopping, it's usually fairly simple. A purchase is a success, whereas with online dating particularly, there are lots and lots of different things that we might consider a success. So is a like a success, which is a unidirectional preference? Is a match a success, which is a bidirectional preference? Is a relationship a success? So within our data sets, usually users go through this process when they decide to find a partner. They search using criteria that they've decided on. They look through a list page. They look at individual profiles. If they find somebody they like, they press the like button. The other user can see that they've been liked. And if they choose to like back, that's considered a match. If they choose not to like back, that's considered a nope, which is our negative evaluation criteria. And then after users have matched, they can message and they can meet. And obviously, ideally, we would like to use something like a relationship as our evaluation goal. But because it's very difficult to get that data, we use likes and matches as our binary indications of unidirectional and bidirectional preferences. So to predict personal attraction using images, we use a Siamese network, which is the thing. We tried a number of approaches, and this was the thing that we found was most successful. And Siamese networks are usually used in, for example, face detection software, and are able to identify small distinctions between faces. And perhaps intuitively, this also works fairly well for predicting attraction. So our input is 2 images which have a relation to a single user. So either 2 images that are liked by a single user, or an image that's liked and an image that's disliked by that user. And the output is 1 or 0 respectively. And the Siamese network has 2 symmetrical CNNs, which create embeddings for the image. And the learning is based off the difference between those embeddings. And using this data, our system learns pretty successfully to differentiate between 2 liked images and a liked image and a disliked image. So we trained using 200,000 pairs of face images, alternately a pair of liked images and then a liked image and a note image. And as I said, the system learns the difference between these. And it's worth saying at this point that our data set is very clean. Pairs manually checks each image to ensure that it contains only the face of the user posting the image. So there are no group photos, no photos with friends. And we also used automatic face detection to ensure that all of the photos in our data set did contain a person and weren't just photos of mountains or deserts or whatever people had decided to post up. And using this model, we were able to design a recommender system that predicts whether 2 users will match or not, which is the end goal of reciprocal recommendation, to predict a match rather than just a unidirectional like. So for candidate users, for example, A and B, we compare B's photo to A's previously liked photos, and A's photo to B's previously liked photos. And this gives us a number of scores from our Siamese network. We aggregate these scores using a random forest aggregator trained on different data. And this gives us 2 unidirectional preference scores from A to B and from B to A that indicate unidirectional preference. And we aggregate these 2 scores using the harmonic mean, which is fairly standard in reciprocal recommendation and has been shown in our research last year to produce a fairly good approximation of bidirectional preference from unidirectional scores. So we ran 2 tests. We tested against, as I said, the best-in-class content-based reciprocal recommender system, Recon, which uses categorical data to make recommendations. And we also tested against the best-in-class collaborative filtering reciprocal recommender system, LFRR. So against Recon, our system performed significantly better. Recon actually performed very badly on our data set. And we consider that this might be because, or it's probably because Recon was originally trained on a dating service that contains only categorical data and doesn't contain any photos or free text information. And these are the things that likely that people mainly use to make their decisions. So just a few short numbers. The area under the curve, as I said, significantly better, and the best F1 score at the highest point of the curve, also about 10% better. We also tested against LFRR, which was the best-in-class collaborative filtering algorithm, and we found that LFRR did do significantly better, given a large amount of data. But it tends to be that, especially in online dating, the cold start problem is a very big deal. People decide whether to stay on the site or leave the site based on quite a small number of interactions and quite a small amount of time. And we found that ImRec did perform significantly better in cold start situations. So even where collaborative filtering is an option, it's likely that our system could be part of an effective hybrid model that works against cold start situations as well as when there's a lot of data. So in conclusion, images are a predictor of personal attraction. This model is proof of that. And I think that's a very interesting result, not only for computer science, but also for social science. And as far as we could find, this was the first demonstration that you can learn attraction using images. And we can model this using a Siamese network, as I said. And ImRec outperforms previous content-based RRSs and also improves on cold start results from collaborative filtering. In the future, I think it would be very interesting to look into potentially a multimodal system that takes into account also free text content, user profiles, and that kind of thing, and incorporates the categories that Recon uses to see if we can do even better than potentially collaborative filtering solutions using the very rich content we have on online dating services. And it would be interesting to confirm these results on other data. Certainly some dating services like Tinder emphasize decisions based on images very, very heavily. And I think it would be interesting to see how these results performed in that context as well. Thank you.
Thank you, James, for a nice presentation. And we have a couple of questions.
Good.
So question 1, in your paper, you mentioned that images are of low quality and have filters pre-applied. Have you quantified the influences of such bad images on ImRec?
We haven't quantified the importance of those kinds of images exactly, and I think it would be interesting to do so. I think that ImRec probably acts. I think that a bad quality image is also important information in users' decision, in that users might also make their decision based on the quality of the image and not just on the person in the image. So I think it's important to incorporate those images and not exclude them. But I agree that it would be interesting to examine exactly the effect of something like a filter or the quality of the image on how popular someone is or how likely they are to be liked by a specific category of person.
Okay. Another hard question. What kind of biases do we see in this domain? There might be popularity bias related to race, body type, etc. For such cases, how can we make these systems consider fairness, especially to minorities?
I think that's also a very interesting question, and as you say, an extremely important question. It was a question that we did want to study, but unfortunately that was very difficult to study with our data set because Pairs is a Japanese language website, and all the data we had was Japanese, and 99.95% of the registered people were Japanese. So it was hard to study the effects of those kinds of factors on this system. But certainly, if you were to deploy this on a service with a very broad diversity of users, it would be something that we would have to take into account. Popularity tends to be less of an issue, especially if you use an aggregator that biases against two scores with a high differential, like the harmonic mean, because very, very popular users tend to end up with a lower unidirectional preference relation from them. And so they tend not to be recommended over and over again. But again, there have been solutions. For example, I think 2 years ago, Kleineman presented a paper at RecSys on systems that eliminate popularity fairness. And there's no reason they couldn't be incorporated into our system.
Thank you. And did you check to see if there were any significant correlations between the text profile data and likes that you could add to the model?
That is actually what we're looking at the moment. We're looking more deeply into free text profiles and ways of modeling that to potentially make a multimodal system that incorporates text and images. And so hopefully I'll be presenting that next year, maybe.
Okay, we are waiting. How balanced are the likes and dislikes? Could this imbalance have an impact on the metrics you are measuring?
It potentially could, yeah, and that would also be something worth investigating. There tends to be a gender discrepancy in likes and dislikes. So for some reason, men tend to send more likes and women tend to send more dislikes, and that's reasonably well proportioned actually within the context of this data set, obviously. But yeah, it would be worth investigating, certainly, I agree.
Okay, that's an innovative question now. Have you experimented with guns that create synthetic faces as a means to model user face attraction preferences?
I haven't, no, but that sounds fun. I will look into that. Is that GANs, GUNS?
GAN, yes.
Okay, I'll look into it.
Generative.
Thank you.
Yeah. Have you tried this model in a country with mix of multiple races?
As I said, no. Unfortunately, I haven't been able to do that. And obviously, it's often quite difficult to get access to dating data sets because of the privacy issues involved. But I would love to do that. And if anybody has access to that kind of data set or is willing to share it, I would be very happy.
Okay. Thank you so much for answering all the questions and great presentations. Thank you again for all the speakers in this session. And this will conclude the session, and see you in the poster session next. Thank you.